In this video, we will do some examples of the Fundamental Theorem of Calculus Part 2. So I want to start off with the integral from 1 to 9 of x squared plus 1 dx. So we did this integral using Riemann sums, and when we did that, we got 752 over 3. So now we're going to tackle this using the Fundamental Theorem of Calculus Part 2, which says when we have a definite integral, which represents an area, we can handle it by taking the antiderivative of this function. So antiderivative of x squared, that will be x to the third over 3 using a reverse power rule. And an antiderivative of 1 will be plus x. And then what the Fundamental Theorem of Calculus says we have to do is we have to plug in the 9 and then plug in the 1 and subtract. So I'm going to introduce some notation that indicates that. So let me first put a bracket around this. So I'm going to write a big vertical line, write a 1 here and a 9 there. So I want to note that when we write our antiderivative function, capital F of x, and I put this vertical line, and then I write a down there and b up here, this means plug in the b first, and then subtract what we get when you plug in a. All right, so let's do that. All right, so if we plug in 9 into this, we will get 9 cubed over 3 plus 9, and then I got to subtract what we get when we plug in the 1. So I got to make sure I put a parentheses around this so I don't forget to distribute my negative sign. And if I plug in 1, we get 1 cubed over 3 plus 1. So simplifying, 9 cubed is going to be 729. And then let me do this minus 1 cubed will be minus 1. I'll have that all over the 3. And then outside of that, we'll have this plus 9 minus 1, which becomes a plus 8. So this simplifies to 728 over 3. And then let's get a common denominator. The 8, if I multiply it on the top and the bottom by 3, we'll get 24 over 3. And adding these together, we get 752 over 3. And that's our answer. That's the same thing that we got using Riemann sums, just a whole lot quicker. So FTC Part 2 is much more efficient. It is much more efficient than Riemann sums. So now that we have this technique, we might ask, well, why even bother with Riemann sums if we were just going to introduce the Fundamental Theorem of Calculus, which would make finding areas so much quicker? And the answer to that has to do with the fact that to prove the Fundamental Theorem of Calculus, we needed the idea of a Riemann sum. So the Fundamental Theorem of Calculus is really rooted in understanding Riemann sums and why they work. Okay, so I want to make one note before we do some more examples. And that's when we do a definite integral, we don't need to write the plus c with a definite integral. So with the definite integrals, we don't need to write that plus c, since they would cancel. They would cancel when you subtract. So for example, in the problem that we just did, we would have gotten 9 cubed over 3 plus 9 plus c if I plug in the 9, and then minus, if you plug in 1, we would have gotten 1 cubed over 3 plus 1, and then plus c. And then when I subtract, the c here and the c here would have canceled, and that's why we don't need to write the plus c when we do a definite integral. Okay, but when we do an indefinite integral, that's when we just had an integral like this, and then I write my function. There I do need a plus c, because this means a general antiderivative. All right, so let's look at some more examples. So example 3, we have this integral from negative e to negative 1 of 2 over x dx. Okay, so let's do the antiderivative of a function. So this will be 2 times the antiderivative of 1 over x. That is ln absolute value of x. Then I write my vertical line, put negative e down here and negative 1 up there. And now I'm going to plug in. So I'll get 2 times ln absolute value of negative 1. And then minus, I plug in negative e to get 2 ln absolute value of negative e. So I can simplify and get 2 ln absolute value of negative 1 is just 1, minus 2 ln absolute value of negative e is just e. And now these I can evaluate. This is 2 times 0 minus 2 times 1, because ln of e is 1. Okay, and this is 0 minus 2, which is negative 2. And that's our answer. So let's just verify that this makes sense by drawing a picture. So if I draw a picture of the graph of y equals 2 over x, so the graph of this looks like the graph of the function 1 over x, which has a piece over here and a piece over here, but multiplying the whole thing by 2 just scales the graph or stretches it vertically by a factor of 2. So we are finding the area over the interval from negative e to negative 1. So negative e is here somewhere, negative 1 is there. Remember, e is roughly like 2.7-ish. So that's how I know negative e is smaller than negative 1. So we want the area between our curve and the x-axis over this interval. Okay, and if I shade that in, it looks like this. So this whole region is below the x-axis. So it makes sense that our area should be negative. And that's what we were getting with our answer. We got a negative value. So that's good. All right, let's do another example. Okay, so this next example says, well, true or false, if I have the integral from negative e to positive 1, of 2 over x, we'd get the same thing. We'd get negative 2 by using the fundamental theorem of calculus. I want to first give you 1 minute to try this. So pause the video in 4, 3, 2, 1. Pause it for a minute to try this question. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about a minute. Let's talk about it now. So if I were to do the same thing that I did above, the only difference would have been I would be taking the absolute value of positive 1 instead of negative 1, but that would give me the same thing, so it seems like I should get the same answer. But if we look back to the fundamental theorem of calculus, one of the things that it says is, my function f needs to be continuous on this whole closed interval from a to b. But if we look at our function, the function 2 over x, I can see from the graph that this is discontinuous at 0, and that is part of the interval that we are now looking at, because we're looking at the interval all the way until 1. So as a result, this is false, because I can't use the fundamental theorem of calculus, and this question says that that's what we were using by FTC. So this is false, because FTC part 2 doesn't apply. It doesn't apply here, since f of x equals 2 over x is not continuous. It is not continuous on our interval from negative e to positive 1, because it is discontinuous. It is discontinuous at x equals 0. So I want to end this example with a note, which is that this type of integral is called an improper integral, where our function is discontinuous somewhere in the interval. It's called an improper integral, which you would see in the next calculus course. So this we would cover in Math 1B. Alrighty, so let's end this video with one last example. So we have this integral from 0 to pi over 4 of secant of t times secant of t minus tangent of t dt. So I first want to give you 2 minutes to try this. Pause the video in 4, 3, 2, 1. Pause it and try it for 2 minutes. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about 2 minutes. Let's talk about it now. So to take the antiderivative of this, I'm going to first distribute the secant of t. So I'll get integral from 0 to pi over 4, and we'll get secant squared of t minus secant t times tangent of t, dt. And now we're ready to take the antiderivative, because the antiderivative of secant squared, that is tangent, because the derivative of tangent is secant squared, and then minus antiderivative of secant t times tangent of t, that would be secant t, because the derivative of secant is secant times tangent. So let's put a bracket around this. Let's write our vertical line. And I'll write a 0 and a pi over 4, because I got to plug those in. All right, and plugging in pi over 4, we'll get tangent of pi over 4 minus secant of pi over 4. And then minus, now I got to plug in 0. So let's put a parentheses around everything. And I'll get tangent of 0 minus secant of 0. And I need this parentheses so I don't forget to distribute the negative sign to these terms, because I'm subtracting all of what I get when I plug 0 in. Okay, so if we work this out, tangent of pi over 4, that is 1. Secant of pi over 4 is root 2, using unit circle. And then minus within the parentheses, tangent of 0 is 0, minus secant of 0 is 1. Okay, so this double negative becomes a positive, and I'll get 1 plus 1, which is 2, and then minus this root 2. So we get 2 minus root 2. So in terms of our goals for this section, we finished our last goal, which is being able to apply FTC Part 2 to evaluate definite integrals, to compute the area under a graph.